Scientists often forget that science is a creative process. And because it is a creative process, it has fits and starts. I think partly we get confused because we like to think of ourselves as so rational and having a plan. And it's also because of the way that we write papers, which is retrospectively, we tend to craft them so that they look very deliberate because it's easier to tell a story that way. But that's not the way science feels on the ground. And it's not the way that it happens on the ground, in my mind, or in my experience. And it has these periods where you've gone through the best exercise that you can to come up with a good plan. You start to execute your plan, and something changes. For instance, you've done an experiment that you thought you were going to be able to interpret, and you can't. So this can be incredibly frustrating because you've put in a bunch of different efforts into it. Maybe it took a bunch of time, maybe it took a bunch of, thought about how to design it. Maybe it's a really horrible experiment that wasn't that long but just was really awful to do. But whatever it is, right? You've done it, you're invested in it, the data is not interpretable in the framework with which you set out to do that experiment. That is biology teaching you something. And so it's really important to take those kinds of failures seriously.
Failure is maybe even a critical element of success, that the freedom to really succeed big requires that we also have the freedom to fail. In baseball, it's okay if you fail at the plate 7 times out of 10, you can be a superstar, right? And I think in science, we need to accommodate that sort of attitude. And so one of the things that I've thought about in the science policy work that I do is looking for ways so that we can begin to, if not celebrate failure, that's a little hard to do, but at least understand the essential part that it plays in being able to do something big and important.
I think it's interesting to pay attention to what people are saying when they say failure is an important part of science, it's a necessary part of science. Usually they're talking about going through a period of failure, but not residing there, right? That failure is sort of a transition state that gets you to where you want to go. What I see is that, unfortunately, at times you see students who will get used to going to the lab, trying something out, having it not work, and then going home at the end of the day and having a sense that that's what science is that process of failure. That actually doesn't take you anywhere. It doesn't take us closer to that apprehension of the truth and the reality that is sort of the fundamental goal, I think, of science. And so in that sense, failure is, in my mental imagery, it's a verb. You pass through failure, right? By doing the failing, you get somewhere else, and you learn through the process of extricating yourself from that position of failure.
A lot of times we have periods where things are flowing, and then there are periods where things get stuck. And I just want to highlight that science, in my experience, cannot be done without getting stuck. And I would even say there's a kind of stuckness that it says, finally, we're stuck, because that time is a time where something about our basic assumptions isn't working. And that is a prerequisite to discover something truly new. So sometimes I say, if A is the question and B is the answer, then research is a straight path. The problem with this schema is if the experiment doesn't work, it's perceived as something wrong with the universe and creates this extra stress, not only the frustration. So I teach my students a different schema that I think is more realistic. I say A is the question, B is the answer, and we get going. And then experiments don't work. The path twists, turns, right, left, until we get to a place linked with negative emotions. And here comes the word we call the cloud. It's a cloud of research. You can be stuck in the cloud for a distribution of time that has a long tail. It could be a day, a week, a month, a year. You die, you're reincarnated as a scientist, you're still in the cloud. But if you have enough support, then sometimes through the mist of the cloud, you can see a new answer, C. Let's call it C, and then you decide to go for it. And experiments don't work, but you get there. and then you publish a paper, A, arrow, C. Now the cloud is an inherent part of research because it stands as the boundary between the known and the unknown. Because in order to discover something truly new, at least one of your basic assumptions has to change. Otherwise, it's not new. And that means that scientists, we try every day to bring ourselves to this uncomfortable place, the cloud. I noticed that I put B in the land of the known because we knew about it when we started. It's our grant proposal or PhD proposal. It's very important to have a good, solid B because it's our direction of where to start. But if we keep things wide enough, when we get to the cloud, we stand a larger chance of finding C, which is almost always more interesting, fruitful, amazing, opening than B.
Many of us who have been doing science for a long time can think back to a time when we had a terrible setback scientifically, and it led to some peripheral discovery, a realization we really weren't moving toward initially. It was the setback that sparked a realization that was extremely helpful in moving the science forward. When I was, this was probably in my third year of assistant professorship, and I had my first postdoc, and she was doing an experiment. And she was supposed to be measuring how synaptic transmission was reduced, blocked by different concentrations of cadmium, all right, because cadmium is known to block synaptic transmission. This is a very well-established phenomenon, and it was just, we were just interested in getting the quantitative measurements of how much different concentrations of cadmium were blocking synaptic transmission. She started doing the experiment, and the cadmium wasn't blocking the synaptic transmission. And this is, a violation. It's like holding a ball in the air and letting go of it and it doesn't drop. I mean, it's just something that's not supposed to happen. And I was bemoaning that fact, and I thought, my gosh, my postdoc doesn't even know how to, perfuse cadmium into the bath. After a while, I started to believe her that actually the cadmium wasn't having that effect. And then I started looking at the data with an open mind, and it was in looking at those results that we started realizing that there was something very special about these synapses, about the way that the neurotransmitter was released that made it apparently less sensitive to the cadmium than we would have predicted. And so that was an interesting example of my own expectations being so entrenched that when a result came in, I saw it as a failure. I saw it as a mistake. We were both harboring this notion that it was experimental error that was giving rise to this result because it so violated our expectations. And for both of us, I shouldn't set this up as though we were at odds with one another. We were actually on the same side throughout. It was only when we came to accept this as a possibility that we were able to see beyond our expectations into a new set of ideas.
And so taking those challenges in your project and thinking about them appropriately, I think is part of becoming a real pro in science. I would say that if I had to describe what you're learning in doing your PhD, you're really learning two very basic things. How to engage with a problem, like a big problem, and break it down into an answerable question and a strategy for answering that question. And the second one is this ability to become very comfortable with ambiguity. And it's hard. Like, being comfortable with ambiguity is not easy. Like, certainty is a much more comfortable place. But scientists, by definition, have to have this like calibrated worldview, right? Where you're able to be like, well, we have some little ideas about how that might work, but they haven't been very well tested. And so I think it's true for now, or true to the best of the extent that I can think about it, or even like, I don't know how that thing works at all. Like, all I have is this weird set of data that tells me that we don't know how to think about it. And being confident enough in your own intellect and work ethic to say, like, I've thought about this as hard as one can, and it is still ambiguous. It takes real confidence. And I think it's a real asset that scientists can bring to the table, that kind of humility in the face of really complicated problems.